Hi, in this video we're going to do some more examples with integrated rate loss and as well as half-life process. So first we have a set of data that shows a reaction, and we need to find the rate of disappearance from t0 to t60. For this question we can use rate of A is equal to negative changing concentration of A over changing time, which will be from t0 to t60 we'll have negative 0.808 minus 1.002 divided by 60, which will give us a number of 0.00323. That's our rate of disappearance, and our rates are always measured in molar per second. Find the rate of appearance of fructose. Let's see what that is. That is this one. Now we can use the molar ratio. First, we just found C12H22, so it's this one. We found this one, now we're looking for this one. The molar ratio is the same, so with that we can use stoichiometry times 1 divided by 1, which will give us 1, and this will also be 0.00323 molar per second as well, because the molar ratio compared to the previous one we just found is the same. So we have to calculate the rate constant for the deposition. Okay, rate constant, we're gonna have to use our integrated rate loss now. Let's see. Okay, so in the problem it's told us it's the first overall order. Now this is very useful because we know which formula to use. If you remember in the integrated rate law for video, first order's formula is natural log of A at a certain time minus natural log A initial is equal to negative KT. Now let's use any numbers we have. ln of, let's say, 60 minutes, which is 0.808 minus ln of initial, which is 1.002, is equal to negative k after and 60 minutes, which gives us 0.08. Now we can do ln 0.808 minus ln 1.002, divide that by 60. So we'll get negative 0.0035865 is equal to negative k, which gives us k is equal to 0.00359. And that will be our k. D, how long will it take for the concentration to drop from this to this? Now again, we can use the same formula we just did. ln, we're looking for time. So it dropped, after a certain amount of time, it dropped to 0.212. And its initial is 1.00233. Is equal to negative k, which we just found, so we don't need to use k anymore. 0.00359 times t. So ln of 0.212 minus ln of 1.00233 equals, divided by negative 0.00323. That gives me 480. So time will be 480. And let's see, our unit here is minutes, so this will be minutes. Oh, number 3, I've got to include units. All right. Here is something that you need to know about rate constant K. Rate constant K. If it's 0th order, you use the unit is molar per second. If it's first order, unit is time to negative first power, depending on what your time is. If it can either be seconds to negative first power, minutes to negative first power, or hours to negative first power. So in this case, I'll just write time to negative first power. Now second order will be molar to negative first power times time to negative first power. Your time can be minutes or seconds. Now you can kind of see a pattern here. First we have m on top, and then we don't have m anymore, and then we have m to negative first. So as you may have guessed, third order will result in m to negative second power times 10 to the negative first. Time is always negative first. And over here when I wrote molar over second, that is actually incorrect. It's molar over time, depending on what your time unit is. And third order is m to negative second, time to negative first, and you may have guessed, fourth order is m to negative third, time to negative first, etc. Time do not change, it's only the molarity concentration that is changing. So now we would know that this is the first order reaction. So first order is time to negative first power, which in this case is minutes, so it's minutes to negative first power. Now finally, let's do E. What is the half-life of the decomposition of sucrose? Now half-life is T of 1/2 is equal to 0.693 over K. Now we just found K, so all we need to do is substitute that into the formula. 0.693 divided by 0.00359 gives you 193 minutes. So the half-life will be 193 minutes. Okay, now we have an unknown compound with the following process A equals 2B. Okay, now we have three graphs. What is the overall order of reaction? So as you look at it on the side, we have ln of A, normal A, and A to negative first power. So what does this tell you? This is first order because it's ln. This is normal, so this is 0th order. And this is A to negative first power, which is second order. Now, how do we know what's the overall order of the reaction? The most linear line will show you the order of the reaction. What is the most linear line? Easily this one. So we know this is a first order reaction. What is the rate law? Rate law is rate is equal to K times the reactant. In this case, we're only given with A, so it's K times A. Calculate the constant K. Now, another way you can calculate the K is slope. So K is the slope. So you can plug numbers into the graph and use the calculator to tell you what the slope is. Now, first we use some points. 30 we can approximate 3.6. 60 we can approximate 3.9. 90 we can approximate 4.2. So we go to stat on our calculator, go to edit, then use 30, 60, 90. Okay, and then in the second column, we use negative 3.6, negative 3.9, and negative 4.1. Now you can go to stat, calculate, and go to linear regression, which is 4, to get AX plus B form. And then you'll get A is negative 0.01, X plus B, which is negative 3.3. And then what is the slope? Negative 0.01x. So that tells you the K is negative 0.01. What are the units? This is the first order reaction again. So our units will be time to negative first power. So in this case, it's seconds. Time in seconds. So it will be seconds to negative first power. Now what is the half-life decomposition? Half-life will be 0.693 over K. So 0.693 divided by our K, which we just found as 0.01 seconds, will be 0.693 divided by 0.01, which gives you 69.3. And let's see, that is supposed to be, that is our half-life of 69.3. Now calculate the A when 150 seconds has passed. So we can use our formula again. Remember our formula? Negative 0.01x plus negative 3.3. All I have to do is plug in 150. So negative 0.01 times 150 plus negative 3.3, which will give you negative 4.8. And now you may get a slightly different answer if you estimated different values than I did, but I used 30 to 3.6, 60 to 3.9, and 90 to 4.2. And these are the numbers I got. So this is the concentration of A, so the unit will be molar. It simply asks you what is the order and what is the rate law. So rate law is rate equals K times reactant, which is X. So that's easy. Now the problem is the rate orders. So first, we're going to do exactly what these three graphs did. We're going to use time for the X value, and X, concentration of X for the Y value, time for the X value, ln of X for the Y value, time for the X, and X to the negative first power for the Y value. We're going to use three different tables. First, we're given, so it's times 0.78 to 80, 420. That gives you 1.881, 1.766, 1.499, 1.339. Next, you're going to have to use ln for the same exact data points. So instead of using 1.881, you're going to use natural log of 1.881, which is 0.6318. The natural log of 1.766 will give you 0.5687. Natural log of 1.499 will give you 0.404798. Natural log of 420 will give, natural log of 1.339 will give you, natural log of 1.3 0.339 will give you 0.2919. Next, we're going to use x to the negative first power. So time will be the same, time units will be the same, 420, and 1.881 to negative first power is 0.5316. The 1.766 to negative first power is 0.566. 1.499 to negative first power is 0.667. And 1.399 to negative first power is 0.71479. Okay, now we're gonna use plug all three into our edit. No, only use one at a time though. So time will be 0, 78, and 280, 240. Now, in case you're wondering, I'm using stat on the TI-84, and you go to stat, edit, and you in column 1 you plug in the x values, which is 0, 78, 280, 420, and in the second column, which is y values, this is where you're putting all of your this one. So when 0 is 1.881, when 78 is 1.766, when 280 is 1.499, and when 420 is 1.339. Now you click stat again. Stat should be somewhere in the middle of your in the middle column of your calculator. You go to stat again, and you click the right arrow to calc, and then you go down to linear regression again, which is 4. And this time it tells you r squared. Now you want r squared to be as close to 0 as possible, as close to 1 as possible. 0.998. Now the closer r squared is to 1, that means the more linear it is. And if your r squared is not showing up, that means you have to go to second catalog, which is second 0, and scroll all the way down to the D. You're going to click second 0 to get catalog and go all the way down to D. And then in D column, in the D section, you can find something called DiagnosticsOn and diagnostic off. Click diagnostic on and click enter. Then when you go back in there, it's going to show you stuff. Now we can go to stat again, calculate, and this time we need to edit the second graph. It's going to be 0.6318, 0.6318, 0.5687, 0.404798, 0.21919. Go to stat again, go to calc, go to 4, enter. That gives you 0.99999. Okay, so r squared is 0.99, which is super close to 1, which means this is more linear than the first one. Finally, we'll go to edit again and go to type in the third column. So we have 0.5316, 0.566, 0.667, and 0.71479. So we'll go to stat again, go to calc, go to 4, and that gives us r squared as 0.99457. Now which one has the closest to 1? It's gonna be this one, which means this is the most linear. Now which one of the orders use ln of x? It's order 1. I should label this. This is order 0, this is order 2, and order 0 you use normal concentration of x, order 1 you use ln of x, and order 2 you use this, as we learned our integrated rate loss. As you can see, this is the most linear, so this is the order of the data set we're given. Thank you for watching.